Hi, my name is Brian Caffo, and this is a lecture on conditional probability for the Coursera inference class. This is part of our data science series, and it's co-taught with my collaborators, Jeff Leake and Roger Pang. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So conditional probability is something that we all kind of know intuitively, but I wanted to cover the formality of it a little bit. Conditioning is an incredibly important concept in statistics. So let's just go through an example that I think we could all agree on. So if you were rolling a die, the probability of getting a 1 is, let's assume it's 1/6. It's a fair die. And then suppose you didn't know the outcome of the die, but you did know that the die roll was odd. So it was either a 1, 3, or a 5. So it was an odd number, and you still want to know the probability of getting a 1. Well, I think everyone would agree that conditional on this new information, the probability of getting a 1 is now 1/3. Right? Everyone would agree on that. Okay? So that's what conditional probability gives you. It gives you the probability conditional on the random variable being in a set. So, and let's just put some formal notation around this. So let's talk about it in terms of events. So let's let B be an event. And it only makes sense to condition on an event that has positive probability. You can't, we couldn't condition on the event that the die is a 7 because dies can't be 7. So that makes that makes things a little bit easier. The conditional probability of an event A, given that B has occurred, then it's just defined as so we use this notation, A given B, is how that is read, probability of A given B, and that's just the probability of the intersection divided by the marginal probability of what you're conditioning on. And then notice if A and B are independent, let's say probability of A given B, right? The probability of this intersection just works out to be the product of the probabilities. Okay, the denominator stays the same. The B's cancel, and you just get probability of A. So that actually makes a lot of sense in terms of the definition of independence, that the probability of A, given the information that B has occurred, is equal to the probability of A. And in fact, some textbooks will use this as the definition of independence, rather than our definition of independence. And of course, it's equivalent. So, but it makes a lot of sense, right? The probability of A, probabilities associated with A, given the information that B has occurred, is just equal to the probability of A, regardless of whether B has occurred or not. Okay, and yeah, so that's independence gives us that. But for non-independent things, that relationship doesn't hold, and it's given by this guy right here. Oh, sorry. Then it's given by this guy. Okay. So let's just go through our example to show that the arithmetic works out. Okay, so B is the event that it's a 1, 3, or 5. A is the event that it's a 1. Probability of a 1, given that the roll is odd, is the probability of A given B. That's the probability of A intersect B divided by the probability of B. Now A is a subset of B, right? So the probability of A intersect B is just the probability of A. Okay? Divided by probability of B. 1/6 is the probability of A. 3/6 is the probability of B, right? The three numbers. And so the probability is 1/3, just exactly like what we thought it would be. Okay, so very, very famous equation is so-called Bayes' rule. And Bayes' rule basically states what it gives you is, notice what we want here is the probability of B given that A is occurred. And sometimes we want probabilities like that, but all we have are kind of access to things like probability of A given B or probability of A given B complement, things where B is the conditioning event, okay? Bayes' rule gives you the way to flip these probabilities around, what you're conditioning on. It's an amazing little formula. So probability of B given A is the probability of A given B times the probability of B over the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. Let's just, kind of prove it, show it real quick. It's super easy. But notice, I just want to point out, right, that's given B, that's given B, that's given B, and then these are all just marginal probabilities associated with B. So the idea is that all you need is both the A given B things that you know plus the marginal probability of B to execute Bayes' rule, and then you can kind of reverse the arguments conditioning on A instead of B. Okay, so let's just so probability of B given A is equal to the probability of A intersect B divided by the probability of A, okay? And here's A, here's B. Okay, so the probability of A is equal to this area, probability of A intersect B complement, plus the probability of A intersect B, right? So that's A intersect B complement, A intersect B, okay? And this guy we can just simply write as probability of B given A. Oh no, I gotta erase no, I'm just gonna scratch it out. I don't wanna erase everything. Probability of A given B times the probability of B. Okay? Right, and that's just by definition. Okay, so let's just look at this denominator, right? So here we have probability of A given B times the probability of B. And this guy we can just now write as the probability of A given B complement times the probability of B complement plus the probability of A given B times the probability of B. Okay? And that's that. So now that's arrived right back at that formula. I think I reversed the order of those two things in the denominator, but it doesn't matter, right? It doesn't matter what order you add them in. Okay, so that's proving Bayes' rule. Let's go through an example. The most famous example of Bayes' rule is in diagnostic tests. So we're going to use just some funny notation. We're going to let the plus symbol to not mean addition, but to mean that a diagnostic test is positive, and the minus symbol be that it's negative. And D complement be the event that the subject has or does not have the disease or the condition being tested. It doesn't always have to be a disease, of course. So the sensitivity is the probability of a positive test given that the person has the condition. And the specificity is the probability of a negative test given that the person does not have the condition. And these are usually reasonable things to be able to estimate, right? You take a bunch of, let's say it's a blood test for HIV or something like that. You take a bunch of people that you know to have HIV, sample their blood and give the test and then determine how many positives you get. And same thing with the negatives. You take a bunch of people that you're quite certain do not have HIV. Now there's a whole science to doing this so that the way in which you get the sensitivity and specificity are representative of the people you want to then use Bayes' rule on to evaluate the result of a positive test. So there's a whole science that we're not going to discuss, but we're going to just use this to estimate or to show an example of using Bayes' rule. But I would be remiss if I didn't say there's an entire world of complexity to these kinds of problems apart from just being able to execute Bayes' rule. Okay. So what we want to use is Bayes' rule to get now the positive predictive value, right? The probability the person has the disease or condition given a positive test result. That's what the person's really interested in if you have a positive test result. Or similarly, the negative predictive value, the probability of not having the disease given a negative test result. Or the obvious other versions of this, the probability of not having the disease given a positive test result, and so on, which is 1 minus that guy. Okay. And then we'll define just the prevalence of disease as the probability of disease, the marginal probability of disease. Again, glossing over the complexities of getting things like the prevalence of disease. Okay. So many people might have heard of these things, especially if you work in kind of biomedical sciences, or if you've taken any statistics class, they love Bayes' rule. So it probably came up. What probably didn't come up are the diagnostic likelihood ratios. So the diagnostic likelihood ratios are the probability of the sensitivity over 1 minus the specificity. See, it's defined right there. And the diagnostic likelihood ratio of a negative test is 1 minus the sensitivity over the specificity. We'll show you why in a minute these definitions are useful. So So let's go through an example. So a study comparing the efficacy of HIV test reports on an experiment that concluded an HIV antibody test had a sensitivity of 99.7 and a specificity of 98.5%. So probability of positive test result given the person has the disease is 0.997, and the probability of a negative test result given not having the disease, the specificity is 0.985. Okay, all right, you got those under control. Suppose that a subject from a population with 0.1% prevalence in HIV receives a positive test result. What's the probability that this subject has HIV? So probability of disease, we're calibrating to be 0.001, okay? And we want the probability of disease given the positive test result. Okay. So let's use Bayes' rule, right? That's the probability of that guy times the probability of disease. Okay, and then in the denominator, we want this guy again. Okay, there you go. Now, and you can plug all the numbers in, but it's sometimes hard to remember. I always sometimes find it hard to remember what goes in the denominator. So there's kind of an easy way to do that, right? You know that you have to have probability of a positive test result in the denominator. So let's double check. So this, when we multiply these two together, we get the probability of disease intersect positive test result. And this one, we multiply these two together, we get the probability of positive test result intersect complement of disease. These two together, right? Disease, positive test result, right? This guy is this one, that guy is that one, and this guy is that one. Okay, so then you can plug in all the numbers, right? We have all those. The only one, let's see, we didn't say, right, is probability of plus given D complement is just 1 minus this number, 1 minus the specificity. And I think you have all, yeah, and P of D complement is 1 minus that guy. So you have all the numbers you need. Oh, and then I do it on this slide. But, oh, and I actually was smart enough to express that one denominator probability in terms of the specificity, and this guy in terms of the prevalence of the, and sorry, you plug it in, you get 6%. So what we're saying is the positive predictive value is 6% for this test. You might wonder why that's so small. I have a discussion of that here. So the low positive predictive value, it's kind of due to the low prevalence of the disease, so that even if you get a positive test and the test is fairly accurate, it's, the prevalence of disease is small enough to drag that down. Now, on the other hand, suppose this person was known to be an intravenous drug user and routinely had intercourse with an HIV-infected partner. That prevalence is probably not right. So then your number would shoot up dramatically. What's interesting about that idea, right, is imagine if you were a counselor reporting the results of this test to someone. It would be kind of interesting if they gave you that information during the conduct of the test, and you all of a sudden said, "Oh no, wait, your estimate of your positive predictive value is no longer 6%; it's 99%." Now, if you're that person, you might say, "Well, wait a minute, what changed? I mean, I understand I gave you this information, but isn't it what part is related to the test and what part is related to my history?" And that's what I'd like to talk about in terms of the diagnostic likelihood ratios. So there's a part of this calculation that doesn't depend on the prevalence, and you can calculate that, and it depends on the diagnostic likelihood ratios. So using Bayes' rule again, we have this guy and this guy right here, probability, if let's suppose you have a positive test result, the probability of disease is this, and then the probability of not having disease is that, right? So this is 1 minus the numerator, right? So the ratio of these guys is the odds of disease, right? Because it's the odds of disease given a positive test result. Right? So if we took probability of D given positive test result over 1 minus the probability of D given the positive test result, which is equal to the probability of D given a positive test result over probability of D complement given a positive test result. That is exactly the odds of disease given a positive test result. Okay, so that's something clearly of interest. But if you take these two equations right here and divide them, right? You divide these two to get the odds, so that's equivalent to dividing the right-hand side here. This is the same as that. It'll cancel out, and then I'll just show you on the next slide what you get. And you get that this guy, the post-test odds of disease given a positive test, is equal to that guy times the pre-test odds of disease, right? This is just D over 1 minus D, probability of D over 1 minus probability of D. This is the odds of disease with no information about the test based on the prevalence. So what this basically says, this equation basically says, is that the pre-test odds of disease times this quantity equals the post-test odds of disease. So this quantity is the multiplier that no matter what your pre-test odds of disease, this is the multiplier that gives you your post-test odds of disease. So this diagnostic likelihood ratio, that's its role. So it doesn't depend on the prevalence, right? It only depends on this quantity right there. And so what you can say, so if you had this person that was saying, I don't understand why my odds change so much given this information about my behaviors, what the person can say is, well, look, no matter what we think a priori about you having the disease, this positive test means that you're in the light of a positive test, the odds are now 66 times that. It just so happens that if we don't know anything, it's kind of unlikely that you have this disease because it's a rare disease. But if we know something that relates to very behaviors that have a much higher prevalence of disease, then your post-test odds will be a lot higher. But regardless of your pre-test odds of disease, your post-test odds of disease are 66 times that, given the light of this positive test. Okay, so that's the objective part. That's the objective part of the equation. So let me just finish with a couple of more comments about this. Another thing I often get when discussing these things is, what's the meaning of the probability of disease given a positive test result when discussing it in the context of an individual person? They either have the disease or they don't, so this probability must be 0 or 1. So that's a fair argument. But what I would say is this probability calculation is done in the context of, suppose I were to consider a population of people like the person I'm talking to, and I were to ascertain this probability, this proportion among those who had a positive test result, the proportion who had the disease, in a population sense. If I were to do it infinitely many times, then this would be the probability. So it goes back to this interpretation of frequency probabilities in terms of kind of fictitious repetitions of the experiment. So when you're describing this to this person, yes, it is true, they either have the disease or they do not. The probability that you're giving them is calculation that is a contextual calculation related to this idea of fictitious repetitions of giving this test to a population of people. So you could answer to that person if they said, well, wait, I either have the disease or I don't. Why is the probability 6%? You can say, well, if I were to give this test to lots and lots of people similar to you, the percentage of them with a positive test result that actually had the disease would only be 6%. That would be your answer. Now, if you're a Bayesian, that's how you can interpret Bayes' rule as a frequentist. If you're a Bayesian and you actually want to interpret Bayes' rule as a Bayesian, as a subjective Bayesian, then it's easy. Your probability is a belief. You're saying, I had a belief that was represented by P of D that you had the disease. The positive test result was the data that updated my belief. Now this guy is my new belief, and that's encoded by this idea of 6%. So for Bayesians, it's a little bit easier. For frequentists, you have to think in terms of frequencies, in terms of fictitious repetitions of the experiment. So I always get that question, so I thought I'd describe it. The last thing I want to mention is, again, this idea of kind of, estimating things like the sensitivity and the specificity, and what the meaning of, how you can interpret them given how you estimate them. So, so take this specific example of HIV. If you were to, in the calculation of your sensitivity that you use here, if you were to have sampled lots and lots of people who were in very late stages of the disease, or maybe those who had progressed to AIDS and were in the late stages of the disease, it's not clear that this sensitivity would be the relevant sensitivity for a person who would be at the very early stages of the disease, the kind of person who might be going for a test, or in a screening procedure where you were testing lots and lots of people through routine blood tests collected for other reasons. Those would be a totally different population than the population you used to collect the sensitivity. There's sampling issues in doing this. And so all of these things combine into making this kind of if you really want to execute these kinds of problems in practice, there's more to it than simply executing Bayes' rule. But for the purposes of this class, we just want to teach you about Bayes' rule. And so you can do it so you can kind of work along your way towards some of these more complicated issues.